Hey there, everyone. I'm Brendan,
And I'm Christian.
and we are here to share our story about building StackCan's advanced analytics workspace to rapidly deploy modern and open data science capabilities in the face of this global pandemic. I do product management and a dash of architecture for the project, so I'm going to spend the first half of the presentation talking about how we approached our problem and leveraged some key public cloud services to take some exploratory work and flesh it out into a usable product in about 15 business days. Christian, on the other hand, is a data scientist who is both a primary user and a direct contributor to the Advanced Analytics Workspace. So he's going to do the much cooler half of this presentation where he shows these tools in action. So let's get started. First, let's consider this silly thing I ran into on Twitter. I find it captures the essence of how most of us have been feeling since March. It seems that when you take a great sense of urgency, an increased tolerance for risk, and add a pinch of necessity, you can get some really interesting and innovative results. For us, this data science platform was one of those results. So it's been nice to find a bit of a silver lining to what is otherwise a pretty dark cloud. Anyway, with this kind of frantic innovation in mind, it shouldn't surprise you to see the challenge we were given by our chief statistician. We were asked to offer data and analytics capabilities to no less than 200 internal and external researchers, and to do it right now. Now, on top of that, we also didn't have access to our typical resources in our cloud environment because everything usually gets mediated when we're working from home from a VPN. And we didn't have the infrastructure at the very beginning of the pandemic to support an entire organization working from home at the same time. So we also had to figure out how to do this with everyone working outside their usual environment on personal equipment. So how do we do that? Let's talk about partnership. With all these hurdles in front of us, it was pretty clear that we weren't going to succeed by trying to go it alone as a development team. We needed infrastructure work, platform work, and application development to happen all at the same time. We also needed to know whether we'd taken the right direction on decisions almost immediately as we made them, which is feedback that can only come from people with a bunch of subject matter expertise like Christian. So what we did is we assembled a single multidisciplinary team from across StackCan. We pulled in members from our own development teams. We brought in our top experts from Cloud Native who focus on technology like Kubernetes. We added our best data scientists, particularly those with substantial IT expertise. And we joined up with digital innovation as well. What's really important to understand here is that we didn't just form a partnership in the sense of regularly meeting or communicating between teams. Here, each individual, regardless of where they came from in the organization, became a member of a unified team, working in the same sprints as a direct contributor to the platform. We learned a lot from taking this approach. And while this model is not without its challenges, you'd be hard-pressed to find a way of building a more effective team. Now, you clearly can't take people from every single role in your organization and cram them together into a single team. There's still a lot of other groups we need to work with. User experience, security, accessibility, communications, support, the list goes on. For these types of relationships, we learned that it is best to engage these partners as early as possible. If partners come in late, they're implicitly sort of reviewing decisions and work that were done without their expertise. By engaging early, partners get to be part of the whole story, and you'll put out a better overall product because of it. For Advanced Analytics Workspace, we were not perfect in doing this, so we got to see both sides of that coin firsthand. Early engagement is better. So let's talk about process. A good process should ensure that the absolutely necessary things are always there, and then it should get completely out of the way. And for us, less is more. In our case, we took a bare bones approach to Scrum methodology, which worked really well for a distributed team with hectic schedules. We did sprint planning, retrospectives, and daily stand-ups, and pretty much left it at that. The sprint planning was good for people whose schedules were disrupted by family requirements due to the pandemic. By planning the work in chunks, we knew what to expect in terms of delivery, at the same time giving developers the freedom to do that work on whatever schedule worked for them. And the Scrum format of daily stand-ups meant that contributors could share the information out of band when necessary, so the team could stay reasonably in sync even if some people couldn't make a stand-up. Back in March, we actually started with 1 week sprints because things were changing drastically by the day and we needed to be able to react in time. 1 week sprints gave us that agility we needed, but came at the cost of relative overhead. After half a dozen sprints or so, the situation grew more stable, and we had enough data to support switching to the 2-week cadence we currently enjoy. And that's an important point, actually. We only change or add to our process to address real issues supported by evidence and not theoretical ones. And that evidence comes from trends we see in our sprint retrospectives. In terms of development practices, we adopted GitLab Flow, which is an awesome and really lightweight workflow for software development with Git. And we work in the open. We built the analytics workspace using nearly 100% open source software, and in turn, we open sourced the entire platform. All of our code is available on GitHub. For example, here you can see one of our example Jupyter notebooks that helps users learn to interact with our object storage. In total, there are over 25 repositories under the StatCan GitHub org that make up this platform, and you can go check them out right now. Our management is also done in GitHub, like most open source projects. So we use issues with standard labeling practices and Kanban boards to maintain and prioritize our backlog, as well as planning and tracking our sprints. Continuous integration has become a de facto requirement for software development, and it's pretty cool if you can manage to do continuous delivery as well. Internally, we would usually use GitLab and GitLab CI to accomplish this, but as I mentioned earlier, we didn't have access to our usual cloud resources when we started building this. So we ended up turning to GitHub Actions to accomplish CI/CD, and it worked out reasonably well. What was really important for getting a product deployed quickly with CI/CD was infrastructure as code. We use Terraform to provision all of our cloud resources, as well as much of the platform layer within Kubernetes. Because of this, our cloud native experts were actually able to provision a brand new environment from scratch in a matter of hours. So if you aren't already, get your infrastructure into something like Terraform and automate it via CI. You won't regret it. Now let's get to the product itself. The Analytics Workspace is a complex distributed system, but it's built on a few simple core principles. First, Kubernetes is a fabulous orchestration system, so we leverage it as a unified control plane. So whether we're running an application, injecting credentials safely into your environment, or integrating with an Azure managed service, we want to use Kubernetes to control that. Second, we want to strategically leverage Azure managed services to reduce our operational burden. We want to manage data access, but not disks. We want to manage pod scheduling, but not cluster autoscaling. and we want to manage application permissions, but not authentication. We use Azure Kubernetes Services, or AKS, to take a bunch of cluster management off our shoulders. Azure Managed Disks back our Kubernetes persistent volumes, and object storage takes care of some of our data lake needs. We use Azure Active Directory for our auth needs, and it also acts as an OpenID Connect provider, which gives us the basis of single sign-on across the various components of our platform. We were also able to leverage its B2B functionality to be able to add guest accounts from outside our organization. This lets us support authentication and authorization of external users and manage that in exactly the same place as we manage our own internal users. By using these services and Kubernetes and layering on open source projects like Kubeflow, Jupyter Lab, Minio, and MLflow, we were able to quickly create an integrated set of components that provide essential capabilities to our data scientists. Using the Advanced Analytics Workspace, a data scientist can create Jupyter Notebook environments, each with configurable CPU, memory, and GPU resources with just a few clicks. When the platform needs more resources to satisfy one of these workloads, new VMs are transparently added to the cluster, and the user's workload is automatically scheduled once they're ready. Those who want a more traditional experience or specific powerful desktop tools like QGIS or Visual Studio Code have access to a full virtual desktop experience delivered directly through the browser. They get the power of a fully functional Linux desktop environment, and we get to manage it just like any other container within our Kubernetes cluster. Those who are ready to level up their analysis can leverage pipelines to create reusable analysis components, to parallelize their workloads, and to create repeatable experiments to improve models over time. So that's it for me. Thank you for listening. If you'd like to know any more, feel free to contact me. It's brendan.gadd@canada.ca. I'm always happy to share. And now, as promised, the cooler half of this presentation, Christian, our lead data scientist, is going to show some of the amazing things that can be done with these tools. So take it away, Christian.
Now I would like to talk about two application cases of data science on the Advanced Analytics Workspace. I work on different data science projects, and I'm glad to be able to leverage the platform for two of our projects. The first one is with the goal to automatically detect construction sites on satellite images. We hope to dramatically reduce the cost of the identification and the categorization of construction sites across Canada. And to do that, we employed big data processing methods of satellite images, deep learning for computer vision, as well as geospatial analysis. All those methods were possible on this platform. The results are a scalable image processing pipeline, which is able to process in parallel thousands of square kilometers of Canadian satellite images and apply machine learning models on it. And the result is quite good. As you can see on the left side, we have a tile of a satellite image. On the right side, we have the prediction shown here, the footprint of the construction sites with its boundary. The compute infrastructure is really the key to enable this project. First, we build a customized containerized environment with Docker, which includes all the open source software we need, including the deep learning stack. In the next step, we created what we call a pipeline processing notebook server, which has a high CPU and memory and allows us to process, to pre- and post-process images. We additionally did analysis, geospatial analysis with QGIS on satellite images. The solid code For the pre and the post processing, we wrote in Visual Studio Code. Most of the code is written in Python. And so after we've done this, we generated a training set which we used for our deep learning on a few GPU notebook servers, in which we set up the servers in a way so that we have a V100 GPU for each notebook server available. And the great benefits were that we were able to get going very fast, had a very easy setup of the infrastructure and click together all the components we needed, all the memory and CPU, and the optimal allocation is also a big benefit, as we can shut down servers and save costs and overall optimize our waiting time. Additionally, we were able to leverage a full stack of open source software without any barriers to enable the work. Now I would like to demonstrate this work through some concrete presentation. Here we are connected to the analytics platform. On the left side, you see the different options, including pipelines and notebook servers, which we're leveraging. Different notebook servers are running here on the left with images and resources. And the first step for us was to pick from different environments per server: remote desktop connection, Jupyter Lab, or Visual Studio Code. When we built this pipeline, we wanted to build good code inside Visual Studio Code, which is also version controlled. And we did some work on with notebooks, with Jupyter Lab notebooks, and did as well work to look at the images provided by the data provider in detail, as you can see here in the browser. Once we finished this work, we created GPU instances, and those GPU instances have the same setup, where we leverage Jupyter Lab to run our deep neural networks, and had this work again version controlled. And also we are connected to an object storage, which allowed us to share data between the different notebook servers effectively. Now I would like to talk about the second project at hand, which is the goal to automatically detect information in large web-based information. And so our analysts are typically looking for business information, especially in COVID-19 time. It's important to get faster and more granular data. So we built an automatic system for this. This included components such as the near real-time processing of incoming textual information from APIs, the deep learning application of models on this data, as well as the crucial information extraction. And the result which we provided to our clients was an up-to-date database with daily ingestion of text, as well as effective search capabilities through this database. We leverage Elasticsearch for that, and as well as to access this information in an aggregated manner through visualizations and dashboards easily through the browser. To enable again this project, we were leveraging another component of the advanced analytics workspace, which are kubeflow pipelines. Those allowed us to build components of information, data extraction, transformation, and ingestion, which could be scheduled effectively, developed in Python, and then deployed of those pipelines. And they ended in the last step into the ingestion in Elasticsearch. We did also deep learning on a separate notebook server to detect the kind of information with advanced deep learning models and natural language processing. We decided to version control the models and the code using the lifecycle tool MLflow. This is specifically a tool for managing models and for model deployment. The deployment itself is done from MLflow through a CI pipeline on Selden Core, with Selden Core as which helped to deploy the model as an endpoint. An advantage of this of the COVID-19 platform, of the analytics platform, was again to automatize the steps fully. Scaling up and building those Kubeflow pipelines is very straightforward for us data scientists, as we can write those in Python. And also to an easy switch between machine learning models produced and registered, and the switch into production of those models. I would like to demonstrate the application of those in this project. Here you see the economics dashboard, one of the dashboards we built for our analysts, which provide all the web collected information. One can choose from different information sources, different media types, languages, and companies, for example. Labels we have currently, we track branch closure, COVID-19 mentionings, and protective personal equipment. Analysts are able to search through those components and really generate value out of the data which are aggregated. To enable this, we have built these pipelines in Jupyter notebooks, again leveraging this environment with Jupyter Lab, and building pipelines which we schedule regularly. Those pipelines are shown here as an example. We have a first step, which is a containerized environment where we explore and execute a Python script which call APIs and do the data retrieval, the pre-processing, as well as the ingestion into Elasticsearch. Now, after we've done this, we applied models, machine learning models, on the text to detect certain economic information, for example, and we logged this information with MLflow. Here you see recent runs being done, hyperparameter tuning as part of the machine learning, and those allowed us then to compare, for example, in this case, different models with different IDs to then decide which model to put into production. The final production step is then to execute with GitHub Actions a pipeline which is then deploying the model via Selden Core on our Kubernetes cluster. And from there we have called the production model first through Jupyter notebooks via checks, and we plan to also enable the access through the Kubeflow pipeline. Thank you very much for listening, and I hope you had fun watching and following our work. Thank you very much.